Hi students, Professor Nugent here. Let's discuss how to test for heteroskedasticity. We're going to test for the heteroskedasticity of the form that invalidates the usual T and F statistics, given multiple linear regression assumptions 1 through 4 and a linear model where y equals beta naught plus beta 1 times x1 through beta k times xk. The null hypothesis is that multiple linear regression 5 is true. That is, the null hypothesis is that the variance of u conditional on x1 through xk is sigma squared, a constant. If we fail to reject this null hypothesis, we conclude that heteroskedasticity is not a problem. Recall that we never accept a null hypothesis. So we are not accepting that the conditional variance demonstrates homoskedasticity. That is because we are only failing to reject the null hypothesis. We're only failing to reject that this hypothesis is not false. We are not proving that this null hypothesis is true. So we do not accept the null hypothesis. We only fail to reject the null hypothesis. So we conclude that heteroskedasticity is not a problem, not that we have homoskedasticity in the data. Alright, so let's show how to test this null hypothesis. The multiple linear regression assumption 4 implies that the variance of u given all of the x's is equal to the expected value of u squared. So we can rewrite the null hypothesis. As the expected value of u squared given x1 through xk, which is equal to the expected value of u squared, which is equal to sigma squared. If the null hypothesis is false, then the error may be any function of the x. We can assume a linear function for the test. So we are going to assume that u squared is equal to delta naught plus delta 1 x1 plus delta all the way through delta k xk. The null hypothesis under homoskedasticity becomes delta 1 equals all the way through delta k equals 0, so that the errors are not a function of the x's. This can be implemented using an F or LM test. All right, this looks a lot like an F test. And the F-stat can be calculated by hand. The F-stat is r squared of u squared. So we're writing the r squared of u squared. This is the r squared from this regression up here, over k all over 1 minus r squared of u squared over n minus k minus 1. And this k in the numerator represents k restrictions, the r squared u squared, it would be the unrestricted r squared. The restricted r squared would be 0 because we are restricting all of the explanatory variables equal to 0. And that's why k is equal to q. Now, if the p-value for this f-test is smaller than the level of significance, alpha, then you can reject the null. Alright, and this tells us if we reject the null, then some corrective action should be taken. Now, what kind of correction actions can we take if we reject the null of homoskedasticity? You have two options that we are discussing in this chapter. Number one is to use heteroskedasticity robust standard errors. The third option is to use weighted least squares estimation. And I'll throw in a third option. You might use a combination of both. So what we have just discussed is a simple version of the White test, which implements the same procedure using all squares and cross products of the explanatory variables in the regression of u squared. So the White test does the same thing, but in this regression, instead of having just x1 through xk, you also have x1 squared, x2 squared, all the way through xk squared, and you have the cross products. So for example, you have x1 times x2, x1 times x3, so on and so forth. So that is the White test, and this is a more simple version of that. Stay tuned to the next video. We will introduce weighted least squares estimation.